Good morning there, everybody. Thank you for taking the time to attend our quantum computing event for today. Just to get everything started, I'm just going to go ahead and do just a brief overview of what the Developer Student Club program is about, and then I'll go ahead and pass it off to Syed to really give us a really awesome event for today. So if you guys don't know what a DSC is, Developer Student Clubs are student-run communities that are supported and recognized by Google developers. And the DSCs empower students by giving us access to Google platforms, and some of the other programs that they run are the Women Tech Makers, GDGs, and Google Developer Experts. A lot of you guys might be familiar with GDGs. GDGs are like DSCs, but they're just for any professionals who want to join and learn more about Google platforms and technologies. And the mission of Developer Student Clubs is to bridge the gap between theory and practice. And what does that mean? In classes, we learn a lot about theory. So we learn a lot about theories of programming and different developer technologies and platforms. But a lot of the time, we don't know how to apply those into real-world situations and solve real-world problems. So that's what the Developer Student Club does. We come together, we learn these different technologies outside of our classes in an environment that doesn't feel like it's a class. It feels like it's we're all together, we're all learning these technologies with one another, and we're learning more about solving actual real-world problems instead of doing an assignment or something like that. Yeah, so that's really just all I wanted to do. I never said my name. I'm Alex Robinson. I'm the president of DSC FAU, and soon I'm going to be the president or lead DSC UCF. So without further ado, I'm going to go ahead and pass it off to Syed. That is not the slide I want to share. That's from a different presentation. So yeah, I think I'm all good to go.
Thank you for the introduction, Alex. Let me just share my screen. All right. So hey everyone, I'm Syed Farhan from India, and today I'll be talking about Introduction to Quantum Computing with IBM Q experience and also Google Cirq. So a little bit about myself. I'm the founder of Tesseract Coding, an organization set up to teach students and people about new languages, new coding languages, and we focus on giving project-based experience to students. Well, I'm also the CTO of Citriot. So Citriot is an AI and industrial IoT-based startup in India. I'm also doing my electronics majors at RV College of Engineering, Bangalore, and I'm also a Microsoft Student Ambassador from India. All right, so why do we even bother about quantum computing? Let's think about this question right now. We need more and more computing power these days. There are many more buzzwords in the emerging field of technology like artificial intelligence, augmented reality, blockchain, etc. And hardware is really not coping up with it. And the best example is Moore's law dying out. And the current computation requirements are not at all coping up with the hardware. We need more compute power in the domains of metrology, space science, defense, scientific applications, medicine, etc. And then cryptography needs a new face. So if you're talking about classical encryption techniques like SHA 256, 512, AES, these are not sufficient in today's era. We need something more secure and which is break-proof and not classical. Another point that I can talk about is diseases are emerging almost every day now, and we are not equipped to find them. The best example comes from the COVID-19 pandemic. It shows that we are not ready for a disease at a large scale. Drug discovery is very slow in today's era, and biochemical simulations need to be done faster at the quantum level, where there are more than 1 billion states to be simulated, which is not keeping up with the current classical technologies that we have. All right, so the contents of today's talk. We'll start off with what computing actually is, what a classical computer is, and I'll try to contrast it with what a quantum computer is. Then I'll talk a little bit about quantum hardware. Then I'll move towards quantum computing, its applications, and then the heart of this entire talk, which is qubits and its representation. We'll then move towards quantum gates. In particular, I'll be talking about three types of gates: Hadamard, PolyX, and CNOT. There are many more gates, but if you try and understand these three, you can understand the others as well. We then move towards hands-on sessions with Google Cirq and IBM Q Circuit Composer. We'll try and entangle two different qubits. Then, if we still have time, we'll discuss about the Doesch problem and Grover's search. All right. So what is computing? I'd like to ask yourselves these three questions. Is computing a physical or a virtual process? Is it finite or infinite in time? And does it have fixed or infinite number of states? So try and think about this. So it turns out that, for example, if you're taking 4 plus 3, which is equal to 7, you're actually using your mental power here. You're actually using your neurons, which are getting fired up in your brain, which is a physical process. It's finite in time because you're taking some amount of time to calculate it. And the number of states in this case, for example, if you're taking an example of the number of neurons that are firing in your brain and the number of neuron connections that are happening, so the number of states is actually fixed and it's not infinite. You must be thinking why I'm talking about these 3 points, because when we try and contrast with quantum computing, we try and figure out what is actually real and what is not real. We will talk about that in great detail later on. So basic building block of classical computer is a transistor, and you can call it as a MOSFET. And what we are thinking about is a transistor acting as a switch. So MOSFET is nothing but metal oxide semiconductor. So we know that these metals can either be silicon or germanium, and these are semiconductors and they work on field effect. And the modes of operation that we care about are the transistor acting as a switch. So if I tell you that supercomputers or the PC or the mobile phone in which you're seeing this particular stream right now is working on these small transistors, which is just acting as switches, you must actually be thinking how these switches are operating in sync together so that you're able to your computer is able to calculate stuff and also display stuff in great detail. So another example of basic computing device is IC7404, which is a simple NOT gate. So everyone is aware of NOT gate. You give the input as bit 1 and it gives you the output as 0. You give the input as bit 0 and the output comes out as 1. And this entire thing is being implemented using simple MOSFETs, which was discussed in the previous slide. So that's how basic computing device is being made in classical computing. All right, so bits are nothing but zeros and ones in classical computing, and they're used to store a lot of information. So, and they are actually processed using logic gates, classical logic gates in classical computers, and information is processed by a sequence of bits. So if you are playing a high-tech game in your system, you must be thinking, how are these zeros and ones helping me play this really compute-intensive video game? Or how is NASA analyzing trajectories of asteroids or new planets that are being discovered every single day? The key is sequence of bits. When sequence of bits together are applied on sequence of logic gates, a lot of stuff can be done in classical bits. And this is actually the drawback, or this is actually the limitation of what classical computer or classical computation provides. So to summarize, physical systems, can be implemented in two possible states, which is nothing but 0 and 1. That's what we are taking from this particular slide. So let's try and understand classical computers, because I will be contrasting quantum computers as well with this. Let me take the pen. All right. So if you're taking an example of 4 plus 3, which is equal to 7, in your mind, you think of 4 plus 3 and you get the output as 7. But how is this actually happening? When you were a kid, you learned about theory of computing. You used to count 3 fingers and then 4 different fingers. And then you counted all of them together to get 7. But that's now not how a classical computer works. It converts these decimal numbers to bits. I'm just trying to summarize. I know you guys know about this, but I'm still trying to summarize so that I can contrast this later with quantum. So if you're taking bits, 4 is equivalent in bits is nothing but 100, and 3 is equivalent is 011. And if you try and add them together, you will get 111, which is nothing but the decimal equivalent of 7. So if in memory you're having these two numbers, 4 and 7, somewhere in the memory, you're loading it actually to the CPU, central processing unit. Remember that the memory and the CPU are two separate entities kept at a distance on your semiconductor IC, and the data is flowing or transferring through wires. So if 4 and 7 are going through the to the ALU for computation, and then the value is being computed, and then 7 is coming back as data to the memory, is being stored in memory, and then the address for reading or writing has to be decided. So all of this is actually abstracted for you in classical computers. They have developed to a certain extent where all of this need not be in your knowledge while you're operating or while you're calculating stuff. So in quantum computers, there are various ways in which you can construct computers, quantum computers, and there is a way wherein you don't have to separate the CPU and memory. Take an example of the human nerve cell. It computes stuff and it also stores stuff. It has CPU and memory together in one cell. So you don't have to transfer stuff using wires. That is one way quantum computers can be constructed. There are ways wherein companies are also moving towards this kind of classical architecture for quantum computers. So quantum computers really do have an edge in this area. So to understand qubits, you need to understand what vectors and vector spaces are. You have studied this in high school. I'm just summarizing it because qubits are nothing but state vectors. So qubits are the vectors are mathematical objects which have both magnitude and direction. We all are aware of that. What is a vector space? It's nothing but a set of vectors which corresponds or which follows certain operations. So if you say that vector space over a field F is valid, you need to follow these two conditions. I won't be talking about the math behind this because it is beyond the scope of this session. The first one is the operation to add two vectors is closed. The second being operation of multiplying vector with scalar is closed. So if it follows these two operations, then you can call a vector space of a field F to be valid. All right. So what are actually qubits? Qubits are nothing but core components of quantum computing. So in classical computing, we had bits, zeros and ones, but quantum computers and quantum computing, we have qubits. And if you talk about amount of information that can be encoded, so if you have two different bits, let's say 0 and 1, how much information can you encode in them? If you have two different registers, if you studied about registers and bits, you can store or encode only information of bit 2. But if you're having two qubits, this would become 2 raised to the power 2. This would become 4, the data width that can be stored or the data width that can be processed with quantum systems becomes 4. Now, if you have 2 raised to the power 10, this would nothing be equal to 1024. So just to contrast, if you had 10 bits, you can store and process only 10 data of bit 10. But if you have quantum systems or you're using quantum computing, if you had 10, you can process 1024 states. And this is possible due to superposition. What is superposition? So if you're taking this kind of a sphere and okay, let's not talk about the sphere. Let's talk about the states. So you can see the symbol over here, which is surrounding 0, which is nothing but the ket notation, KET ket notation, which means that this is a 0 qubit. And then we have the 1 qubit. Superposition means a qubit can be in a state of both 0 and 1 simultaneously. So that's one of the plus points of having quantum systems. And then qubits are inherently probabilistic. So if you have two identical quantum systems or qubits, and you're trying to measure the value of those qubits, so at the end, even if it was in a superposition of any manner of 0 or 1, it's gonna come out as a classical 1 or 0. That's after measurement. So when you're measuring a qubit, it loses its property, it loses its value and becomes 0 or 1. So what is meant by this inherently probabilistic? If you're measuring it twice, if you're measuring it thrice, if you're measuring 4 times, or if you're measuring 2 identical qubits, then there is a chance that they will turn out not to be equal. That's another probabilistic phenomena that has been acted upon on quantum systems, and we are actually using it to our benefit in quantum computing. I'll talk about that later on. So before I go ahead, let me talk about basis. To understand the actual math behind qubits, let's talk about basis. So if you have a vector, in this case, it's this dark blue line, which you can see in both cases. It's nothing but a vector in this case. And if you're trying to get the components of this vector in the x, y, and z axis, You can see this is the light purple line, and here in this case it's the red line. If you try and add these components, the sum of these components will give you the same vector, exactly the same vector of the same magnitude and in the same direction. So you can say that these set of values of x, y, and z, they can be multiple sets, are known as the basis of this particular vector system. All right, so let's move on to the main part, the most important part, qubit representations. So qubits are nothing but represented as this kind of 2D column vectors. Alpha and beta have to be complex numbers, and it needs to follow this normalization condition, wherein modulo alpha squared plus modulo beta squared should be equal to 1. If it follows this particular condition, then you can say for every set of alpha and beta that satisfies the condition, this particular 2D vector will be a qubit. So here are a few examples that I can give for qubit vectors. For example, 1, 0 vector. If you try and plug in these values into this normalization equation, you will get 1. It will satisfy the condition. Similarly, you can have 0, 1, or you can have 1 upon root 2, square root of 2, and 1 upon square root of 2. There are multiple number of sets that you can obtain with this normalization condition. Okay, so if you're trying to contrast the classical qubit system, classical bit system 0 and 1, and you're trying to get the equivalent in quantum systems. So this is the accepted way. 0 bit in quantum system is represented as 1, 0, and 1 bit is represented as 0, 1 vector. So if you take a circle of unit radius, and with the positive x-axis being your qubit 0 and the positive y-axis unit being qubit 1, and then if you're taking an arbitrary vector, in a unit vector in any direction, in this case, let's say it's making an angle theta with the x-axis. So this vector is nothing but the psi vector. This can be written as alpha times 0 qubit plus beta times 0 qubit. 1 qubit, wherein alpha and beta are complex numbers in this case. And this, if theta is equal to 45 degrees, then you can make out easily that alpha and beta are equal to 1 upon square root of 2. Simple math, right? Simple trigonometry. And then if you have another vector over here, which is minus 45 degrees. So if you have minus 45 degrees, then your alpha will be 1 by root 2 and your beta will be minus 1 by root 2. And we call this as minus qubit state. And this particular state where theta was 45 degrees, you call this as plus qubit state. So these are the basic states that we will be working with: 0 qubit state, 1 qubit state, the plus qubit state, and the minus qubit state. So yeah, what is a quantum computer? Let's talk a little bit about history, how quantum computers came into being. So people started simulating classical environments and classical systems using classical computers early on. Then there were issues with simulating, quantum systems with classical computers. So that's when it was thought about that why don't we go ahead with a quantum simulation? On a quantum computer. That's when quantum computers came into existence and people started investing to a great deal. That's when people realized that quantum computations can have much more applications than what they had earlier decided or what they had earlier discovered. So a quantum computer is nothing but a system which computes qubits as per the quantum algorithms. And we know that classical computers are made up of semiconductor oxides, metal oxide semiconductors at normal temperatures, but quantum computers are made up of different set of metals at very low temperatures. I'll talk about that. And then information is processed and stored in quantum states of matter. So let me give you an example of this movie, Source Code. Everyone is aware of this movie, I'm sure. So Jake Gyllenhaal every time goes back into the past and tries to change the future. So what's actually happening in that quantum system. There is a new universe being created for every time he goes back into the past. So this actually has some kind of implication. So theorists and physicists believe in a certain way of multiverse interpretation, wherein every single time a quantum state is being measured, a new universe is being split up. a new universe is being created. So it's like having infinite number of universes for every single object or for every single environment that we are having. Further discussions on this topic are beyond the scope of this session, but we can surely discuss in person later on. Okay, so quantum transistors, for example, if we have transistors in classical systems, we need to have something analogous in quantum systems as well. That's where quantum transistor steps into practice, and it is known as SQUID. So full form of SQUID is nothing but superconducting quantum interference device, and this entire thing is made up of niobium, a metal, at superconducting temperatures. So let me tell about this temperature. It's less than millikelvins. So if you have a temperature less than millikelvins, then it means that it's much or far more colder than the outer space, not universe, sorry, the outer space. So think about this low temperature in your particular lab, in the lab of IBM, or in the lab of D-Wave Systems, or in the lab of Honeywell. We are actually moving towards a lot of progress in this by using metals, or by using things that are at a much higher temperature than the superconducting temperature. You must be thinking, how are qubits simulated? So if in qubits we have superposition of both states of 1 and 0, right? So that is being simulated using magnetic fields of +1 and -1. If you can actually create a superposition between these two states, and thus your qubit system is being ready. So here it is mentioned, in the SQUID's full form, we have interference device. What do you mean by interference? Let me talk about a double slit experiment, which almost everyone has studied in their physics class in middle school. So let's take a small gun which is shooting out bullets. You have two different slits, slit 1 and slit 2. You have a backstop and a movable detector to detect these bullets once they are being fired. So now if you're covering your slit 2 and you're letting only the bullets to pass from slit 1, and if you're trying to move the movable detector, you are able to see this kind of probability distribution, P1. But then if you are trying to close slit 1 and moving the bullets from only slit 2, you will see P2 kind of probability distribution. So based on the math, if you try and add these two probabilities, you get this kind of probability distribution, P12. Now, if you are repeating this exact same experiment again with light, so light in a form is a wave, and if you're trying to do the same experiment, you will get this kind of crests and troughs again, and then this kind of pattern will be formed, wherein the intensity will be maximum at the center. The intensity keeps decreasing as we move further away from the center of the screen, and then you will find a lot of dark spots in between. Dark spots are nothing but destructive interference, and these bright areas which you can see are nothing but constructive interference, which means that the rays which are coming out from these two slits are actually interfering between each other. Now, if we repeat this experiment with an electron or an electron gun which is shooting out electrons, what do you actually observe? We might think we will be getting this kind of probability distribution P12 because electron is a form of matter, but instead we get this kind of probability distribution wherein electrons are being observed in these kind of areas. There are areas where electrons are not observed at all. So this kind of spooky behavior is nothing but dual nature of matter, wherein matter behaves as both as waves and matter itself. So this is the exact, or you can say, explanation behind why qubits or why quantum systems behave as they behave. All right. So you might be thinking, what about having multiple qubits in a particular IC or in a particular chip? So if you are trying to transfer the information between one qubit to the other, there might be information loss. Why are we having the superconducting metals? Because of thermal noise, the quantum state gets disturbed, distorted, and in some cases it even gets erased. So if you are using wires or couplers, normal wires, copper wires, in no way can we conduct, in no way can we create a quantum IC, but instead we need to use couplers which are themselves superconducting. So what I'm trying to make, my point that I'm trying to make here is, if quantum systems are given a thermal noise or any other kind of noise, they lose their state, and then the entire computation goes haywire. It needs to be maintained at that particular temperature under certain conditions. So before we move on to hands-on coding sessions with IBM Q and also Google Cirq, I'm going to talk about a few applications of quantum computers so that you can get more interest into this field. So I'm sure that everyone here has tried out at least one algorithm in machine learning. So I'm going to talk about support vector machines right now. So if you have to classify two different classes and draw an optimal separator, a line between them, what would you actually do? You can see that there are blue dots and red dots. You would just randomly draw a line in between, let's say line L1. And then what you're actually doing with a support vector machine algorithm is you're taking the nearest point from either classes, from both the classes, drawing a perpendicular. Same thing goes for the red dot as well. You're drawing a perpendicular here. And then these two are your support vectors. And based on these support vectors, you try and increase the margin between the data on both sides. If you're trying to increase the margin, you formulate a mathematical equation, and then you try and reduce the error. And once the error cannot be changed any further, you know that, okay, this particular line that I have drawn is an optimal separator, which is shown on the right side over here. So now if we are, okay, so in this case, we had a line equation y equal to mx plus c. It's a one-dimensional equation. But now if we have this kind of a system wherein you have to separate the dots, red and blue dots, you have to draw either a circle or an ellipse or anything that is two-dimensional in nature, geometrically two-dimensional. What if you have to draw something which is having degrees of up to 10 or 20 or 30 in some scenarios, and these dots are of more than millions or billions in quantity, which happens in real-world systems. So you cannot actually compute this using classical system. It becomes really tedious. It takes years to process some amount of information. So one such solution is you try to shift this. You try to map this nonlinear data into a 3-dimension, for example, a higher dimension. In this case, we are having a 2D scenario. We try and shift it to a 3D, and then you draw a hyperplane. So a plane's equation will be much more simpler than that of an ellipse or any other circle or a distorted figure. Hence, the entire computation becomes really simple. So what's in it for quantum computers? Anywhere where you have to shift to a higher dimensional space, remember that quantum systems can process information on an exponential level. So if you had 10 qubits, you could process 1024 amount of information. So shifting to higher dimension is piece of cake for quantum computers. This is one of the applications in machine learning that I'm showing you. There are multiple algorithms that can be optimized using quantum computing. Google has also come up with quantum machine learning in TensorFlow Quantum, wherein some of the layers are being processed by quantum simulators and the others by classical computers, which really make things faster. All right, another plus point of quantum computers is their parallelism. We all know about it because quantum systems, a qubit can be in a state of 0 and 1 simultaneously. You can infer from it that if you're having a person, he can be in multiple positions at the same time. Take an example of the Maze Runner. If Thomas and Minho could be at multiple different positions at the same time, they would be able to find the exit at a much faster pace. Small example of maze solving is, okay, let it just load. Okay, so if you have to find the path in a maze, instead of finding single paths every single path at once, you can go through all the paths at a single time itself. So you can see that the paths are branching out every single time. This is possible with quantum computers, and they can do it really well because they're made to do this stuff. There are many more applications of quantum computers, like in AI, quantum machine learning, as I spoke about, quantum cryptography. Then there's a lot of applications in stock market analysis and prediction, like financial and business modeling as well. Then weather forecasting can be made more accurate with quantum computers. Particle physics, since particle physics is a very close brother of quantum simulations. I mean, quantum simulations are required to a much greater extent in this domain. Quantum computers prove to be a really a really good thing for simulations of physical systems at quantum level. There are multiple applications in healthcare. So we can take examples of drug discovery, which can be made much faster, biochemical simulations, which can be made much faster and on a much higher scale using quantum computers. All right, a little bit about quantum gates. So quantum gates are nothing but matrix operations applied to qubits. So for example, if you have a matrix 2 cross 2 matrix and you're applying it on qubit 0. So we know that qubit 0 is represented as 1 0 vector. We had seen it earlier, and then you finally get an output which has to be of unit length. And if the quantum gates are not unitary, you will get some other arbitrary output which will mess up your entire quantum system. So we define quantum gates as matrix operations which are unitary in nature and are applied to the qubits to get a final desired outcome. All right. So I would request you guys to go to quantum-computing.ibm.com and create an account over there. It's pretty simple. Just with 2 clicks, you can create an account. So I would like to show you guys about how IBM Q can be used to simulate quantum circuits. All right. Let me just share my other screen as well. Okay. Is my screen visible, Benjamin?
Yes, it is.
All right. So you can sign in with your IBM ID or using Google account, LinkedIn. I personally use my GitHub account. So it's just a single click away. You just have to sign in and go to the Circuit Composer. So just give it a minute or two to sign in. Okay. So I'll be going to the Circuit Composer and then create a new circuit. Just give it a name. I'll just give it test 1, 2, 3. Just keep this ready and then we'll come back to it. All right, guys. So let's talk about the first gate, the Hadamard gate. As you can see, the Hadamard gate is defined as a matrix, 2 cross 2 matrix, 1, 1, 1, and -1, followed by 1 upon square root of 2. So if you were to apply this Hadamard gate to qubit 0, it would look something like this. You would write this matrix. Please apologize my handwriting, guys. I'm using a mouse for writing. Okay. So qubit 0 is represented as 2D column vector 1 0, and then it's nothing but matrix multiplication. You all know how matrix multiplication is done. So 1 into 1 plus 1 times 0 is nothing but 1, and then 1 times 1 into -1 times 0 is again 1. And yeah, 1 by root 2 will follow every single time. I'm just avoiding it so that I have to write less right now. So you can write this whole thing as 1 upon square root of 2. This whole thing can be written as 1 0 plus 0 1. Okay, so it can be seen that 1 0 is nothing but qubit 0 and 0 1 is nothing but qubit 1. You can also write it alternatively as 1 upon square root of 2 into qubit 0 plus qubit 1. Now, this state is also known as the plus qubit state, which was shown earlier in the PPT. So plus qubit state was nothing but when your vector is making 45 degrees from the positive x-axis. All right. Now, if you were to apply the Hadamard gate on the qubit vector 1, then you would get the minus qubit state. And The best part about the Hadamard gate is, if you were to apply the Hadamard gate to the output which you obtained when you applied it on qubit 0, for example, if you're applying it on qubit vector plus, then you will get back the 0 qubit, and vice versa. You can test out Hadamard gate of qubit 1 gives -8. You can test it out later on when you have time. All right, let's get back to our IBM Q experience. You had created a new experiment, test 1, 2, 3. All right. So we have different quantum registers. By default, it gives you 5 quantum registers. We just need 2 right now. So quantum register Q of 0 and quantum register Q of 1. This is nothing but your measurement instruction. So if you place the measurement instruction over here, you can see that you will be getting the 0 classical value back. Okay. So yeah, if you go to settings, and then you can select the number of classical registers that you want. Right now it has 5. You can go to 2, or you can just synchronize it with quantum registers that you have. So what we are actually doing, if you go to the code part, code section, you can have a look at it. This is nothing but the Quasm code for it. We are including the QLite 1, and then we are creating quantum registers of bit 2, and you're creating classical registers of bit 2. And then you're trying to measure this particular Q0, and then trying to show the output on the classical bit. Now, let's apply the Hadamard gate to this. Let's have a look at what we get. If you try and have a look at the state vector, you can see that you get 0.707, which is a real number in this case, and 0.707, which was nothing but 1 by root 2 of 0 vector or 0 qubit plus 1 by root 2 of 1 qubit. Now, if you would like to execute this, just save the particular experiment and then run it on the simulator. You can also run it on live quantum computers if you want. There's one live in Melbourne with 16 qubits available. I think London also has one, Burlington, Essex, Monk. I'm running it on a Quasm simulator. If you want, you can run it on a real quantum computer as well. And I'm selecting the number of shots to be 1 in this case. So what are number of shots? Number of shots is the number of times you're running an experiment. If you're dealing with probabilistic states, you need to have the number of samples, right? So the shots are nothing but the number of times you sample your experiment. For now, I'm just sampling it 1 time. Let me just sample this. Okay. It takes a few seconds to get your result, because it's actually sending out this particular operation to the quantum simulator running in IBM Cloud, and then fetches back the result. So it takes a few seconds. Just wait for it. Yeah. So the result is ready. Yeah. So you can see that we had taken 2 classical registers. So the state is 0, 0. And then if we are trying to measure the state of the qubit, try to recall what I said when we are measuring any particular qubit. If you're measuring a qubit, it will lose its quantum state. So if you're passing it through the Hadamard gate, it needs to be in an equal superposition of both 0 state and 1 state. But instead, what is actually happening? If you're measuring it, it collapses to state 0. Now, if you run it with 1024 shots, you try and run it with 1024 shots, you will try and understand why quantum systems are probabilistic. Okay, let's give it a few seconds. Yeah, it's ready. So you must be seeing that you will have 2 different bars, wherein 0 state is almost 50% and 1 state is almost 49%. If you try and increase your number of shots or the number of samples for the experiment, you can see that 49% will try and converge to 50, and 50, which is greater than 50 over here, 50.4, will try and converge to 50%. So it will be like 50% and 50%, which will somehow match with this probability, wherein you are having an equal superposition of both 0 and 1 states. All right, let's move on to the next gate. Okay, before that, let's have a visual of the Hadamard gate. If you're passing the off state, which is nothing but the 0 qubit through the Hadamard gate, you will get a mix of both 0 and 1 state, which was the plus state. And then if you're passing that mix of 0 and 1 again through the Hadamard gate, you get the off state back. This was a small visualization. Let's move on towards poly X gate. So as you must be expecting, this is how a gate operation is being applied to a qubit. So it's nothing but your matrix 0, 1, 1, 0, followed by the 0 vector, which is nothing but 1, 0. If you try and multiply this, you get 0 times 1 plus 1 times 0 is nothing but 0. 1 times 1 plus 0 times 0 is 1. This is nothing but equal to the 1 qubit state. So you can clearly see that x of 0 qubit gives you 1 qubit. If you try it with x of 1 qubit, it will give you the 0 qubit. This is nothing but an equivalent of classical NOT gate. Okay. So a small visualization, if you're passing the on qubit state, which is 1, it will give you the off qubit state and vice versa. Pretty simple. Okay, this is a little bit tricky. Controlled NOT gate. This is the matrix for controlled NOT gate. It's a 4x4 matrix. Don't worry about it. It's 4x4 because we are applying it on 2 different qubits. What is actually happening here? It flips the second qubit. The CNOT gate will flip the second qubit. So if A is qubit 1 and B is your qubit 0, then if A is equal to qubit state 1, then your second qubit will get flipped. But if A is equal to 0, then your second qubit will not get flipped. There's a small quantum truth table for it. You can see that qubit state X has a qubit state of 0. Nothing happens to the second qubit state. But then if your first qubit state is 1 and 1, you can see that your second qubit state has flipped from 0 to 1 and from 1 to 0. And here's the classical equivalent of this control NOT gate, wherein you just doing an XOR operation of XY, and then X is as it is. Okay. So if you want to try out let's delete this. If you want to try out the poly X gate, try running this with 1024 shots. Okay, give it a few seconds. Till then, we can try and run the CNOT gate as well. Okay, here the output is here. So the initial input was the 0 vector, and finally we get the 1 vector. We are only considering the first classical bit, which is C of 0. So it adheres to our result. So now if we are trying to use the CNOT gate, okay, if we're trying to measure this, try running it with 1 shot only. What you will get currently is 0 because your first qubit, the control qubit, is 0. So the second qubit will not get flipped. But then if you're trying to flip the first qubit, and the second qubit will also, if you're trying to have 1 state instead of 0 state, your second qubit will get flipped. You can try that out later. All right, let's move ahead. Let's move on to 2 qubit systems now. So if you're having 2 qubit systems, there are 4 possible deterministic states. You must have guessed by now: 0, 0, 0, 1, 1, 0, and 1, 1. So we call this state 0 to state 1, state 3. And this will be really helpful in quantum entanglement, a small experiment which we will do today, hands-on with Google Cirq. So quantum entanglement was told by Einstein as spooky action at a distance. What actually happens? You take 2 different qubits and then you try and entangle them together. So what happens through their lifetime? They are kind of entangled. They are kind of, communicating with each other. They are linked to each other until and unless they are measured. It's a given that when you measure a qubit system, it loses its state, right? So I'm not talking about the measurement part of it. I'm just talking about the linking part between 2 qubits that we have. That phenomena is known as quantum entanglement. So if you were to take these two qubits and put them at two ends of the universe, there is no way that light can travel from one end of the universe to the other, because universe itself is expanding faster than light. So if you were to keep these two qubits, they will still be linked to each other, which means qubit transfer or quantum entanglement can travel faster than light. In some manner, you can say that vaguely. All right, so I'll just show you the math behind quantum entanglement. It's really interesting. So you don't have to get bored. Pretty interesting math. So what you're actually doing is you have a 2-qubit system. And then you apply the H gate. So I'll just show it to you over here first. You're applying the Hadamard gate first, and then you're applying the CNOT gate, and then you measure both of them together. So this is nothing but you're entangling two different qubits. So what is actually happening, the math behind it? You're applying the Hadamard gate to the qubit system 0, 0, basically to the first qubit. Please apologize my handwriting. So if you're applying a Hadamard gate to 0, we know that you get the plus state, plus qubit state, which is nothing but 1 by square root of 2, 0 vector, qubit vector, plus 1 qubit into the 0 qubit that we had over here. All right. So now we are applying a CNOT gate to this combination. So if we are applying a CNOT gate to this combination which we get, then we know that applying a CNOT gate means the control bit, if it is 1, only then the controlled qubit gets flipped. So in this case, in the first case, we have the control bit to be 0, which means if you're multiplying this 0 qubit to it, it will not get flipped. So you get 0, 0 state, plus you get 1 times 1 state, because it's getting flipped because of the CNOT gate. And the whole thing is 1 by square root 2 times the whole thing. So this is nothing but an entangled system. So what it means is that if you are having, if you name qubits as Q1 and Q2, what it means is that Q1 is somehow now linked to Q2. Okay. So if you're getting Q1 to be 0, if you're trying to measure the first qubit and you're trying to get 0, and then automatically qubit 2 will also be 0. If you're trying to measure qubit 1 as 1, automatically qubit 2 will be 1. You don't have to measure it. You don't have to say it. It will automatically be linked, however far they are. Even if light cannot reach them, even if it's inside a black hole in a certain manner. So this is also known as the first Bell state. There are multiple ways by which you can entangle qubits. One other example is 0, 1 qubit state plus 1, 0, 1, 0. And then 1 by root 2 times. Okay. What this means is if your first qubit is discovered to be 1, the second will always be the opposite of it, and vice versa. Okay. So this is one type of entangling qubits. Here a small example. If you have basis state as a blue color qubit and red color qubit, and if you're trying to measure the first one, which is blue color, and they are entangled using this Bell state, wherein it's the inverse of each other, then the second qubit will always be red color, irrespective of whatever the surrounding is, irrespective of how far it is from the first qubit, etc. Okay. So quantum entanglement has several applications. The first one is super dense coding. So with just one qubit, you will be able to encode a lot of information. It's nothing but related to the exponential amount of information that it can store. Then another application is quantum teleportation, wherein you can actually teleport states. We are not talking about teleportation of human beings or objects. We're talking about teleportation of information. And so what exactly is teleportation? It's like transferring of one thing to another place, from place A to place B in zero amount of time. So that's actually teleportation of information in this case. And it has a lot of applications in quantum cryptography as well. So what happens in cryptography is, in classical cryptography these days, you have a pre-shared key, or you have multiple encryptions, and they can be cracked. But in quantum cryptography, if you're creating a key, or if you're creating an encryption, and if someone snoops in, or someone sees what is inside that particular, or how it is encoded, or if they try to break the encryption, then the entangled state of that particular system will change. You will automatically know about it, and your information can be secured. So there is no way you can break into quantum cryptography in any way. So it has a lot of applications once quantum entanglement is being developed really well in labs. So here's a small example use case of quantum teleportation. So here's Earth on the left side, here's Mars on the right side. So distance between Earth and Mars almost 132 million kilometers, and the communication time. So based on the position of Earth and Mars, thanks to the elliptical orbit around the Sun, the communication time can vary from 4 and 24 minutes. So if you are trying to communicate between Earth and Mars, what you can see is that it takes some amount of time to transfer the data. But then if you're encoding qubits, and then if you're having qubit 1 on Earth, and if you're taking qubit 2 on Mars, and then you're trying to measure what is on, for example, this qubit 2 measures the surrounding of Mars. It for example, takes the images of the surface of Mars, and then you want to transfer that, or transmit that information in zero amount of time. This is possible with quantum teleportation, which is being made possible due to quantum entanglement. Okay, let's talk a little bit about Cirq and Open Fermion. So Cirq is a Python framework which was released by Google AI Quantum probably a few years ago. And what it actually does is it helps you in simulating NISQ quantum algorithms. So it's near intermediate noisy states. So what it actually means is that quantum systems these days have a lot of noise in them. And it's not possible to create a 100% noise-free quantum system which can transfer data perfectly. That's the entire reason why we are having superconducting qubits. So Cirq helps us in simulating real-world quantum systems. Another tool that Google had developed is Open Fermion, and Open Fermion helps in simulating, fermions. Fermions are nothing but very small particles, for example, electrons. So electron-electron interactions at a quantum level. If you want to simulate those things, those kind of chemical or biochemical or physical simulations at a quantum level, Open Fermion is your go-to solution. All right, enough of theory. Let's go to code now. Request everyone to go to this link, go.dacfao.com/circcollab.
And hey, Syed, before we get started with Cirq, we have a couple questions in chat to see if you could quickly answer those. The first question we have is from Xing, and it says, in classical computing, a state is represented by 1 or 0 in the transistors. In quantum computing, how are the alpha and beta determined?
Okay. All right. So I said that a qubit can be in superposition of both states 0 and 1, and to determine alpha and beta. So for example, if you're creating, I'll talk about quantum entanglement. If you're entangling two different qubits, you're initially providing a mathematical equation to it. You're initially providing certain kind of matrix operations. So we had gone through the Hadamard Gate and the CNOT gate to it, and we know that the output is going to be 1 by root 2 times 0, 0 state and 1, 1 state, which is nothing but the entangled state. So if you're trying to determine the alpha and beta in probabilistic systems, you initially look for how the quantum systems have been encoded in the first place. And if that is not the thing, then you have to take samples or multiple samples of the quantum system, run it again and again, and then try to determine these values of alpha and beta in certain manners. I hope I have answered your question. Okay.
We have two other questions from Shing. I'll give you one more question before we move on, and his third question we'll go ahead and save for the end, as well as if anyone else in the chat or the stream has any other questions. So I'll go ahead and ask this question, and I'll go ahead and highlight it. Give me 1 second. Another question that he asked is, do quantum computers require a device to shoot electrons through those two holes constantly, and a detector to constantly detect electrons?
Okay. So if you're talking about the double slit experiment that was performed, it was an experiment to prove the dual nature of matter. And we are not performing this experiment again and again each time a quantum computer operates. So the operation of quantum computers was explained earlier in the slides as to you have a superconducting metal, a metal at superconducting temperatures, and you induce magnetic fields in a certain manner to get the superposition of both states, a 0 qubit state and a 1 qubit state. So yeah, you do not require a quantum computer to continuously shoot out electrons and then continuously detect those electrons. Yeah.
Okay, perfect. I think that's good. We can go ahead and get started with Cirq, and then if we have any other questions, we can go ahead and ask those towards the end.
All right. So yeah, I hope everyone has opened this link. If you go to this particular link, you will land on this Google Colab file. All you have to do is go to File and save a copy in Drive. Since I'm working inside my Drive, I won't be creating another copy. Once you've created a copy, connect to a runtime. It'll take a few seconds to connect to a runtime. People who are new to Colab, I'll just brief you how it works. So you have different code cells. You can run them by either clicking the play button or clicking on Shift plus Enter or Control plus Enter. Okay, and any of the variables that have been used in the cells previous to the other cells will remain in the working environment. All right, let's just click on this and see if our environment is working fine. Yeah, it works fine. I'm printing out Hello Quantum. Okay. I hope everyone is following up. All right, let's move ahead. So next you have to set up the dependencies. So you'll have to install the Cirq Python framework. It takes a few seconds to download it. And once this is done, you will be creating a random number generator circuit. So if you pass a qubit through a Hadamard gate, you will be creating a random number generator of some sorts, and that's what we are trying to create. That's a kind of an introductory note to Cirq. So first things first, you'll import the package, import Cirq. Then you have to create a 9 qubit. Basically, you're creating a quantum register in this case. So that is of size 1. That is why you will enter 0 over here. And then you will create a quantum circuit. So I've just named the quantum circuit as random number generator. All you have to do is circ.circuit. You will get it over here. Circ.circuit. Then run this. All right. And then you will add the Hadamard gate and the measurement tool. So you had seen earlier in the IBM Quantum as to adding a Hadamard gate is not sufficient, but you have to measure it as well to see it in a classical register. So you will just go ahead and run this thing. And then finally, you will just display the circuit. So just print the circuit, print random number generator. Okay. Run this and you will be able to see the circuit. You can see that you're starting out with the 0 qubit state, and then you're passing it through a Hadamard gate. You're applying the matrix operation, and then finally you're measuring it, and you're providing the key as R. So keys are nothing but identifiers for a particular operation or particular circuit, so that later on you can. We'll talk about that later. Okay. All right. Okay. So now talking about scalable vector graphics of this circuit. So you can see that things are pretty well shown here in the IBM circuit. So if you want a similar circuit to be printed, you just have to execute this code cell. What we're actually doing is we are creating an SVG image and writing it to file and then loading it again. All you have to do is use this SVG circuit function and then pass in the circuit name as the parameter, circuit's variable name as the parameter. All right. So let's talk a little bit about quantum simulators. So simulators are nothing but kind of a co-processor with a computer system. So if you're having your PC and you're trying to install a simulator, quantum simulator in your device, it creates a co-processor for it and executes the information, executes the instructions that are being given, and then brings back the result to the PC, and that's how it's been displayed. Since I'm using Google Colab, the co-processor is being created in Google Cloud only. So let me just initialize the simulator. You can initialize the simulator using cirq.simulator command. You must be getting the prompt. Yeah, cirq.simulator. And then you will run the simulator with the simulator.run function, which takes in the circuit and the number of repetitions as the parameters. So let's keep the number of repetitions as 50 for now. Just a random number, you can keep it whatever you want. And then the key has to be the one which we had used earlier. So earlier we had used the key as R. So we will be using the same key here, R. Okay, let's try and run this. So simulating the circuit, you can see that 0 has been demonstrated 30 times, and we have obtained 120 number of times. This is going to be a random number. You can try and execute it multiple times if you want. It's going to come out as a random number. So you've just generated a random number circuit. And then if you want to see the histogram of this particular thing, you just have to execute this code cell, wherein it uses the cirq.plotState histogram, and it takes in the object, the simulator.run object here. You can see the number of times 0 and 1 is obtained. Since it's a probabilistic experiment, it's all about the number of samples that we obtain. So I'm sure everyone would be aware of quantum supremacy by Google, right? So quantum supremacy was actually demonstrated on this 72 qubit bristlecone computer. And this is actually the architecture of that. So what we are actually doing is we are formatting the qubits of the cirq.google.bristlecone architecture, and then we'll finally print it out. Cirq.google.bristlecone, all right? Let me just run this and have a look. So this was the qubit arrangement which was used by Google for demonstrating the quantum supremacy experiment. I'll not get into the details of this experiment as it's beyond the scope of this talk. Okay, so now we'll move towards entangling two different qubits. So we had seen earlier the Bell state, which was 0, 0 vector plus 1, 1 vector. And we are trying to create that here. First things first, you will create a new circuit. So Bell circuit equals cirq.C circuit. And then you will initialize two different qubit vectors, Q0 and Q1. So cirq.line qubit, and then we are defining it of size 2, so range of 2. Then we finally apply the Hadamard gate to it. So all you have to do is cirq.h, and you're applying the Hadamard gate to the first qubit, right? If you remember the Bell state that we had created earlier, it was nothing but the first qubit that we were applying it for. So it's Q of 0, right? And then finally we apply the CNOT gate. And CNOT gate was applied on both the qubits. So you have to do cirq.CNOT and then pass in the arguments Q0, Q1, right? And then finally we are printing the circuit to see how it looks. We are initializing the simulator, and then we are getting the results of simulating this whole thing. Finally, we are also printing the results to see an extra line just for readability. And then we are trying to sample this entire measurement by appending a measure tool, a measurement instruction, and the key which has to be used. Okay, let's just keep the key as Q for now. Then we are trying to sample the circuit with, and then running it with repetition, 20 repetitions for now. Finally, you are plotting the histogram, and the key will be the same one which we had defined earlier over here while using the measurement tool. Let's go ahead and run this particular circuit. Okay, you can see that the bell state was being created. You have the Hadamard gate followed by the CNOT gate. So CNOT gate is represented as something like this. So you can have a look at the CNOT gate better in this circuit, SVG circuit. Yeah. So Hadamard gate followed by the CNOT gate, and then finally the measurement tool with the Q as your key. All right, so what is actually happening? You get the output vector as 1 by root 2 times 0, 0 vector plus 1, 1 vector. They are being entangled. If you're trying to sample the circuit, see the results, you can see that this the 3 state was nothing but 1, 1, and the 0 state was nothing but 0, 0. Try and run it once again. You'll see a different number for 0 state and 3 state, which clearly shows that you are getting a perfect, probability or perfect number of results for the 0, 0 state and the 1, 1 state. To try and print the samples to demonstrate further how this entanglement is happening. This is your first state and this is your second state. If you try and look, 0 will correspond to 0. Again, 0 will correspond to 0. Basically, these are completely identical, which means that they are entangled. And if the first qubit state is 0, the second qubit state will be 0, and similarly for 1. All right. So this was the entire circuit for entangling 2 different qubits, and you've completed level 1 of Cirq tutorial. So now you're equipped to execute quantum algorithms using Cirq. Thank you guys for staying with me till the end. And if you guys have any questions, you can ask it out now, or you can even contact me on Twitter. My DMs are always open, or you can contact me on LinkedIn.
Awesome. Thanks, Syed. I learned a ton of stuff in a little bit of time, but like you just said, I do want to take this opportunity to see if anyone in the stream has any questions about, intro quantum computing questions. If you have something maybe a little bit more specific, like maybe on specific, like on Cirq, maybe Syed can give you some pointers there. I know some people have some burning questions, maybe about the application of quantum computing. So if you guys have any questions, just go ahead and drop that in the YouTube live, and then we can go ahead and get that on the video. And we do have one question from Alessandro, and that is, are there any other resources that we can use to go deeper into the subject of quantum computing?
Oh yes, of course. The QuizKit documentation by IBM is really helpful. So if I can just go to that, go to IBM Q Experience, you can go to QuizKit notebook and resources. So resources are really helpful. They help you get started with quantum computing from the basics, and you can also find. Yeah, so if you just Google up QuizKit documentation or IBM Q's instruction manual or stuff like that, you will find a ton of documentations, ton of stuff to get started with, a ton of videos where you can understand quantum computing and try and apply them here in the Circuit Composer. As for Google Cirq, the Cirq documentation is really helpful. You can start off with documentation of Cirq, cirq.readthedocs.io, and you can start off with installing Cirq on Windows, or you can, if you have issues with the Python, versions, then you can start off in Google Colab itself. There is a tutorial for everything. There are multiple concepts being explained, and yeah, Google has indeed put up an awesome documentation to get started with Cirq. All right. There's also a course on Coursera, Introduction to Quantum Computing, which is really helpful. So it starts off with the math behind quantum computing. So if you're new to linear algebra, I would prefer you learn a little bit of linear algebra and then move on towards that course. Yeah.
Perfect. We do have another question from Shang that says, how would we use the gates to do the comparison of 4 plus 3 in quantum computing?
Okay. So if you're computing 4 plus 3 in quantum computing, it will be similar to as you do in classical computing. The main benefit of using quantum computers comes into picture, wherein you're using the exponential amount of encoding, property of quantum computers, the property of using the parallelism of quantum computers. So I had given you one application of quantum computers. Let's go to the applications. Yeah, I've given you an application in machine learning, support vector machines, or any other applications wherein we have higher dimensional space coming into picture, or wherein we have many number of states that cannot be easily handled by classical systems. That's where quantum computers comes into picture. So it's not like quantum computer can make your 4 plus 3 computation faster. It will obviously make it faster, but that's not the entire point. We are having the point of having quantum computers to solve problems that cannot be solved with classical computers, or which cannot be solved in normal human lifespan time with classical computers. Okay.
All right, we'll just wait for just a minute or two to see if anyone has any last burning questions, and if not, then we can go ahead and call it an awesome event.
Yep.
We've got another question from Ben. He ran the random number circuit, the random number generator circuit, and he got more than one. He got more ones than zeros. Is there any reason for that?
Okay. So the random number generator circuit which I created was not a perfect random number generator. So I just utilized the property of the Hadamard Gate and the probabilistic property of quantum systems. So if you were to use a Hadamard Gate on a perfect quantum system, what you would get is 50-50 of ones and zeros for every single, every batch of samples that you measure. But since quantum systems are inherently probabilistic and they are prone to errors, we will be getting random numbers here and there. For 0, we get a random number of zeros, and ones, we get a random number of ones. And this can be made possible, to converge to equal number of ones and zeros if you increase the number of samples or the number of shots, which I had described earlier. So this is not exactly a random number generator circuit, but I'm just trying to show that quantum systems are inherently probabilistic, and we are trying to use that property to our benefit. There are multiple other ways to create random number generators, but we can discuss that further later on, personally, if you want. All right.
All right, I'll see if there's maybe one more question. So if anyone has any questions in the stream, go ahead and ask, and we'll make that the last one. While we're waiting to see if there's any other quantum questions, someone asked earlier, what's the easiest way to join the FAU Developer Student Club? So the club itself, to officially join, you do have to be an FAU student, but most of our events are public, and all you got to do is participate. And to get on our Discord and our contact list, all you got to do is go to dscfau.com. That'll take you to our website and our main page. And if you're an FAU student, you can go ahead and join through our OWL Central page. That'll make you an official member of the club. Then you can go ahead and click the Discord button. That'll get you in our Discord server, where we will make announcements, and you can ask questions, we can collaborate, whatever else. And you can also get in our contact list, so you will get your email and contact information for future events that we can let you know about. And I think we'll just go ahead and make Alessandro's the last question. And he's just saying, is there any way to contact you if we have any other questions?
Yeah, surely. You can contact me via Twitter or via LinkedIn. I'm also in the Discord server of DSC FAU. And if you have any doubts, you can go ahead and ask there itself.
All right, perfect. I think that's it. Guys, like he just said, if you have any other questions or you need to reach out to him, there are his social handles on the screen. But he's also in the DSC FAU Discord server, like he just said, so you can go ahead and send him a private message or tag him in one of the channels, and I'm sure he'd be happy to help you with that. Okay, guys. It is 11:55, so it's just close to our 12 end time, but we'll go ahead and wrap it up just a few minutes early. So I do want to thank Syed for taking all the time to really teach us all about the basics of quantum. It was really, really informative. I learned a lot. I know everyone else in here learned a lot, and I look forward to learning more about quantum. So thanks so much, Syed.
Yeah, you're welcome. Thanks a lot for having me here. It was wonderful giving a talk at DSC FAU.
Awesome.
Looking forward to more sessions.
Yep, me as well. So with that said, everyone, have a great day, and we'll catch you next time.
Thank you.